Hi, good afternoon, everyone. So I have not yet addressed whatever your doubts were the last time. Sorry for that. For the hybrid scheme. So basically, that is also a scheme for incompressible flows. That is numerical scheme for incompressible flows. I will forward your question to the professor for the session 2 on this one, as I am not trained in that method and I would not be able to answer the specifics of your questions very well. Um, so hopefully he will be able to explain it to you better in session. So now today for the week 8 assignment, we'll be discussing some basic things related to incompressible flows. So the numerical challenge with respect to incompressible flows typically is that there is no density and pressure coupling. So that is problematic. Why? It's because when we have a compressible flow, we have the ideal gas equation, that is PV equals to nRT, and that or like P equals to rho RT in terms of how we use it in CFD. And what that does is that it gives us a relation between the density and the pressure. So therefore, we are able to solve for the field using this extra constitutive relation known as ideal gas equation or any other equation of state. So that luxury is not available with us when we are dealing with incompressible flows because the density is constant. Therefore, we cannot rely on the pressure conflict, like we cannot rely on the density and pressure relations to calculate the pressure. So there are various ways to deal with that. So we'll just come on to whatever was discussed in the current week now. The various ways to deal with that were discussed in the lectures, as well as there are more ways in which researchers have worked around this problem. So coming on to whatever has been discussed. So first things first, we have over here some definitions. The first is vorticity. So now, vorticity is something that you would have learnt in your fluid mechanics class. So it is the curl of velocity, and it is given as this formula right over here. So this is also 2 times the circulation is what you must have read in your fluid mechanics class. Then the second thing we have over here is the stream function. So basically, what is the point of defining something like a stream function? So why we try to define a stream function is that it is used to represent both the components of the flow velocity as one variable. So this makes our life a bit easier because by calculate by solving for just one variable, we are able to get the relations for both u and v. So for the 2D incompressible flows, the governing equations can be written as can be written in terms of this vorticity and the stream function. So that's one way of just writing our governing equations, which is more feasible for incompressible 2D flows. It's not recommended for compressible 3D flows because the definition of stream function as well as vorticity become very fairly convoluted and complex in terms of 3D. And also when we're dealing with compressible flows, it's not always possible to write such a simple relation between u and v since the density keeps on changing, right? So then two algorithms, computational algorithms were discussed in this current scenario. So basically, I'll just mention a little bit of history so that it gives you a little bit perspective regarding why all of this is being done. So, like I mentioned, that whatever doubts you had regarding quick, I was not able to address it very fairly. Why? Because these methods are more geared towards solving for incompressible flows. So now, when the subject of computational fluid dynamics first came about, it was by someone known as B. Spalding. So he was the one who was sort of the pioneer for all this CFD solutions. So now, when the schemes were like when we started to realize that okay, this numerical scheme can be used for solving our flows, what happened that there were two different types of flows that people set out to address. So one is compressible fluid flows and one is incompressible fluid. So our discussions in this particular subject are more geared towards incompressible fluid flows. So in that condition, as I mentioned, that the density is constant with respect to pressure. That is an important consideration. With respect to temperature, it is no change. And basically there is no coupling between pressure and density. So in order to solve for that, we have a totally different approach than how we solve for the compressible fluid flows. So for compressible fluid flows, in case you have ever worked with ANSYS Fluent or any other computational software, you would have seen that sometimes there is a option between density based solving mechanisms as well as pressure based solving mechanisms. So when we are dealing with incompressible flows, we are always doing pressure based um, solving. Why? Because pressure is the only variable over there, density is a constant. Meanwhile, when we are dealing with compressible flows, you have to always go with the density based solutions. So my work and my experience until now has mostly been geared towards compressible fluid flows. I will try to justify whatever incompressible as fluid flows as much as possible. And in case I'm not able to address it in a good fashion, I will be forwarding your questions to the professor for the session. Anyway, so now we are dealing with incompressible fluid flows as you must have seen in your lectures. So first thing we have a simple algorithm. So this was something developed again by B. Spalding and his student Suhas Vedananda. So this simple algorithm, what it does is that it basically solves for pressure linked equations. Once again, there's no density occurring over here, like density related things occurring over here. So this, the full form of this simple is semi implicit method for pressure linked, semi implicit method for pressure linked equations. Okay, so then the equations are linked through pressure, that is the momentum equation basically. So it is used for incompressible fluid flow since there is no density and pressure coupling to evaluate the P. So this is a more of an iterative method where we try to come upon the correct pressure distribution by iterating again and again and seeing if it sort of fulfills our criteria. So then the second method that was discussed was SOLA, that is algorithm for incompressible. It's a solution algorithm, that is its full form, for incompressible flows, which operates on getting a divergence free solution field. So why are we getting a divergence free solution field? Is that by definition, like basically by the usage of continuity equation essentially, we know that for incompressible fluid flows there is no divergence. So divergence in case of a 2D flow is basically what? This. It's this quantity, right? So this is known as divergence. Divergence, I'm just going to put it as D. And for incompressible fluid flows, so basically what is our, just if I don't take into account any other like simplifications, then my continuity equation looks something like this. I'm just going to write in 2D is equal to 0. So this is what my compressibility equation should, this my continuity equation looks like. So now when I'm dealing with these sorts of simplified flows, what am I assuming? First thing first, I'm assuming since the density is constant, it does not change with time. So this term just goes up. Okay. Once again, when we are talking about incompressible flows, we mean that the density is constant with respect to pressure. When there's a temperature gradient, then it's going to change and that complicates things. And in that case, we have to bring in the effect of the energy equation, which for these particular schemes, right now we are ignoring. We are saying that the temperature gradient and all is something we're not concerned with, and there is not much change with respect to the temperature. Right. So, okay. So then this becomes 0 for me. And since my density is once again constant, so this is going to just jump out of the equation. So basically, I'm just going to have something like du by dx into plus d rho v by tau y is equal to 0. So in this case we know that this cannot be 0, this is not equal to 0 because density, that is material density of a particular material, cannot be 0. So therefore we know that this is the quantity that is 0. So what is this quantity? This is also, this is divergent as we saw above. So then basically an incompressible flow is basically a divergence free flow, and this solar method, what it tries to achieve is that from a given set of initial guesses of the u as well as the v, we try to continuously correct it using this pressure correction term, in order to get basically a solution field in which there is no divergence. Right. Okay, so now we come on to the questions that I have today. So the first question is the value of vorticity at point W. Okay, the value of a vorticity at point W if non-dimensional velocity components on grid size are defined as this and this, and delta x is this. What is the value for vorticity? So vorticity, as we found out, was basically this du by dA, du by dy minus dv by dx. Okay, correct. Let's have a look. dv by dx minus. So basically, it's going to be the result of that. dv by dx minus du by dy. So we compute that. So what do I have over here? This and this. Value of vorticity at point W. This. So point W is at wall. So what happens at wall for a viscous flow basically is that U is equals to V equals to 0. Okay, this is the no slip condition. Right. So now I have to find out du by dy. So I'm just going to represent it in terms of a forward difference problem. So in that case, what do I have? Considering that this is this is point 2, this is point 1, I am going to have u at point 2 minus u at point 1 divided by delta y plus um, okay, so this is coming from your forward difference assumption. Right. So what is dv? So v at point 2. So what is v at point 2? It's also 0. So times the total v2 minus v1 4 by delta x. So minus of u2. So over here this is the u1 u1 u2. So basically I'm going to have here 0.01 minus 0 over delta y. What is my delta y? Okay, so there is no, oh, there is no delta y. Value of vorticity at point W. Okay. So this is basically a one-dimensional flow. It's not a two-dimensional flow. So then basically, so what I'm going to do is that I'm just going to not have, then I'm, instead of trying to use this formulation, sorry, this formula, what I'll do is I'll use the definition of vorticity. So definition of vorticity is curl of velocity, right? Curl of velocity. So basically I'm just going to use this delta x into v 1 comma j. Okay, so this I'm getting from simple how we calculate torque as well, right? So that is how we take that. We take this momentum arm, basically this momentum arm, and we take into account the v velocity. So then what do I have over here? So delta x wij 0.1. Or rather I should just have I should just use the thing that I have available to me, that is dv by dx is available to me. So So dv by dx is 0.1 by 0.0005. How much is that? It should be just this. Yeah, 20 it is. Hmm. But basically, we have curl of velocity over here. So since there is no delta, see what my issue right now is that basically if there is no delta y, so whether I should consider it zero, in that case it will go to infinity, but of course that's not an option. So then A should be the right answer. But like curl of velocity, yeah, this should be the right answer. Let me confirm it once. Um, but it will make sense to for one dimensionality to go with what we have over here. Like, yeah, so 20 is the right answer according to the whatever problem I have over here. So basically, if you don't have a delta x, just go with the sorry. If you don't have a delta y, then go with the delta x. Whatever you have, just use that and put it in the formula. But we will have to go with this. Anyway, so then next question is on a solid wall aligned along the x direction, and the non-dimensional pressure boundary condition is given by. Okay, so first we'll just illustrate this. We'll just go ahead and put our wall aligned with this. Okay, and we will go ahead and write our complete non-dimensional governing equations for say for a incompressible. Basically, we're going to have du by s dy is equal to this is my equation if I don't really bother, like if I don't take any assumption. So this is my equation for the x momentum. Similarly for the y, sorry, for the x velocity, for the y velocity I'm going to have, right? So we are considering a 2D flow over here. Then see, when we are asking this question, we have to understand what all assumptions are associated with it. So first assumption is that it is steady. Why is the steady assumption coming? Because basically they've just asked us that in this condition you can see in an option also there is no time factor, and the non-dimensional pressure boundary condition is given by this. This is what my equation looks like, and I'm just going to erase the let me not erase it, I'm just going to cross the time. Okay. Second thing is that when we are talking about something like this, basically we are assuming that this du by dx formula. Okay. So when we are talking about a steady flow, we are also in this condition, in this particular case, we are talking about a completely developed flow. So what do we mean by developed flow? It's that basically this sort of a velocity profile is not going to change along x. So d by dx completely developed. D by dx of velocity is not is equal to 0. So when we are talking about a completely developed flow, do you expect the dp by dx that is the pressure gradient along this direction. Okay, the pressure gradient along the x direction to be 0. There is this dp by dx term. No, we will not assume that, because basically for your flow to be to progress, we need an dp by dx. Okay, so the pressure gradient is what drives the flow, so it's not going to be 0. So then basically, okay, this is something that's not going to be 0. Okay, I don't know. Okay, so the next what we have this v du by dy and dv by dx. So these both terms go away because of our assumption of a completely different flow. So then we have this and this, right? Um, so now if we go with so dv by dy. So now we'll just do like a thought experiment. In this case, like see, you know that v over here is 0, right? And since the flow is not going to be moving outside, it's not intermixing, it's not turbulent, and all of the layers of the flow over here are basically not moving upwards or anyway, there is no this component of velocity, so we can assume that v is 0 everywhere. Okay, so then basically this equation becomes obsolete, and over here this term also goes. So then I'm left with this over here, this expression. Then, and especially at wall, obsolete for wall, that even if I do not assume this v equals to 0 everywhere, v is equals to 0 at wall, and since we need the governing equation at wall, I'm just going to stick with v equals to 0 at wall. I'm going to implement this value v is equal to 0 at wall. Let's not jump to seconds and steps. Then this will become state on the. So basically then I have minus 1 by re into, but in this case also if I open up this del square, basically what I'm going to get dx square plus dy square. And since I've just mentioned that if I'm assuming a fully developed flow, then this d by dx is 0. There's no change to this. So it is 0 equals to minus d by dx. So why I gave this entire explanation with respect to the boundary conditions is so that we know everything is coming from the same place. So there is no magical place that a certain equation or condition is coming from. It's all basically a group of assumptions that we are taking from either observations or from known things, and then we go with an option. Then option A is the right answer. Okay? Right. And if you see that even if you didn't want to go through all of this, you will be able to realize that there is going to be a square term associated, because that this is what is representing the this portion of the equation, that is the viscous one. Anyway, so now we'll move on. This page isn't required. Okay. Next question is, at the inflow boundary condition, okay, of a computational domain. Let's just make a grade first. Okay, if we're talking about a computational domain and I see there are some points kind of discussion going on here. Okay, make a domain right. Okay. Okay, this is just 1D. I'm going to just so I have a domain which looks like this line over here. At the inflow boundary of a computational domain, inflow boundary, I'm going to just tag this as my inflow boundary. Inflow. The v component of velocity has to be prescribed as 0. When using the stream function and vorticity formulation, the boundary condition in terms of phi would be this. Okay. So now we are talking about the formulation, that is the stream function and the vorticity formulation. So we are not dealing with V at all. We won't deal with V directly. V directly. Okay. We deal with either stream function or vorticity. So now over here they have just asked me what the boundary condition with respect to phi is. Okay, so I'm just going to make my grade points. So this inflow, I am considering it as phi 1, that is my stream function value over here is phi 1. Over here it's phi 2, over here is phi 3, and phi 4 and so on. Okay. So now this is my unknown. What is my known? Knowns. So from our initial condition, we will know all other values of, we will know phi 2, phi 3, phi 4, etc. And we have a Newman type boundary condition. Newman. Why do we have a Newman type boundary condition? Will someone tell me? Given that v component of velocity at this is 0, v equals to 0 at it. So why am I saying it's a Newman type boundary condition? What is a Newman type boundary condition? Can someone type in the chat box? Yeah, it's a gradient based boundary condition. Okay, what is d phi by see dx by definition? What is d phi by dx? Yeah, that's great. Thank you, Alfreda. So it's d phi by d6 dx is basically zero. That's what I'm getting. No, 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 not in vorticity. Over here we are being asked for phi. So this is the symbol for stream function, okay, and this is the symbol for vorticity. So from our definition, basically over here, I'm just going to skip back to the beginning. We saw that in case of stream function, d phi by dy equals to v and d phi by dx equals to minus v. Okay. So basically, it is asking me to input a value for v. Okay. So this may have another direction also, that is the x direction might also be considered. I'm just considering this as the y direction. Okay. So bear with me over there. And we are basically dealing with d phi by dx is equal to sorry, this is the x direction, this is the y direction, but I am being asked um, to basically input a value for the v direction. Okay, so v component of velocity, that is why this word component came, because we are not dealing with the 1D system exactly, we are just dealing with a system in which we want the y direction of velocity to be basically 0. Okay, and by definition I know that d phi by dx is equals to minus v. Okay, this is by definition, and since I have a value for v, that this is 0, and again as Vitul mentioned that basically when we have the gradient of a particular value, sorry, a particular variable at a particular at a location, then we are dealing with a Newman boundary condition. One more thing you will note over here is that there are two indices, so therefore it's a 2D problem. Okay, so it's not a 1D problem. I should have made the entire one. So then my y direction is up there and x direction is around the east-west kind of a direction. Anyway, so this is a Newman boundary condition that I have. Okay, because I'm only given value for this at 1. Okay, at the point 1. Hmm. seriously wrong over here. Just okay. Anyway, so then this is what I have over here. This kind of a situation. So what will I do? I will go back to my Taylor series. Okay. And I will try to find an expression for um, 1 minute. Okay. Yes, in this right. Okay. So then I have Taylor series over here. So basically, now that I've mentioned what my knowns are, that is, I know the derivative of phi at 1, okay, 1 comma j. I'm just going to put comma j's everywhere so that we are aware that this is a 2D problem. And I know my derivative in terms of x. Okay, so in all of my options, I can see that this phi 4 doesn't make this stream function at 4 doesn't make an appearance. So I'm just going to erase that. I don't care about it. And what I'm going to try to do is that I'm going to find an expression for d phi by dx at 1 comma j using phi I, which is my unknown, phi 2j, which is a known, and phi 3j. How will I do it? I'm just going to first write down the expressions for this. Phi 2 comma j is equal to phi I comma j plus d phi. This is what I need. 10 phi by x and j delta x plus x square into delta x square by 250. Okay, plus higher order terms. And similarly, I can write for phi 3j. So phi 3j is equal to phi 1j plus again phi 1j so 1 comma j once again, because I want this value, so that's I'm going to stick with this. Square this. Okay, so since the delta x has now become 2 times delta x, that is why this is making an appearance. And I have override just like this. So I'm just going to be unconcerned by the higher order terms. And what I'm going to try to do is that I need to eliminate this. Okay, somehow I need to eliminate this because it's my most significant term. Right. So most significant error term that is. So how can I eliminate this? I can just multiply this entire thing by 4 and then just subtract this. Give me 4 j minus 2j ci 5 I comma j plus my how many times my unknown? 4, 2 times of my this thing unknown. Sorry, this is my known. Because I know the since I this is a Newton condition. This is my known, and this is what I want to find. I comma j plus error terms. Unconcerned by error terms. These error terms will be of order x delta x. So I have this. Okay, let's see what all I have. I have this. Okay, it's 0. So I'm just going to put 0 instead of this. and then from there I can get 4 into phi 2 comma j minus phi 3 comma j by 3 is equals to phi I. So I need to, sorry, phi 1 comma j. So this is what I need. Okay. So I have obtained my solution for the boundary condition at inflow. Is that fine? So let's see which option matches with whatever we've done over here. Which option matches? It's option A. I have a 1 by 3, I have a 1 by 3, I have 4. Yeah, so it's option A. Right. Moving on. At a particular, so hopefully that was okay. At a particular iteration step of pressure velocity correction algorithm SOLA, we are talking about SOLA. Values of the non-dimensional velocity components for scalar control volume ij. So I have a control volume ij. Let us make this control volume. Ij are this. So I have u half. Okay. So this is my u. This is half. This is I plus half. So these values. Ui plus half is equal to 0.9. Ui minus half 7. Uh, J comma K. Again, this is like a three-dimensional case. In this case, if you have noted the what do you call it? The different indices that are here. So, three-dimensional case. So this is, so we have to pay a little bit more attention to this. Okay, fine. This point is this is J J minus half. Where am I giving values for J minus half? Is this B is equal to I'm just not writing the indices which are not changing. I have this for information pieces, and it's asking me that okay, this is also given to me delta x, delta y is 0.5, find the value of the pressure correction term for this set delta Pij at this time. Okay, so here we'll just go back to our and have a peek at the formula that we had over here. Here's this. This is the pressure correction term for the for this kind of a case, and over here. So this is the pressure correction term. This refers to divergence as per the scheme. It is trying to move towards a divergence free solution. This is delta x, the normal, that is the delta, that is the x space step, and this is the time step. So you can just compute it for me. Just giving you di comma j at a particular k is equal to now that you know this, then basically you just have to use your whatever expressions you have for basically u I plus half minus u I minus half I x. Similarly for delta y, you just need to add that up. Please give me a value for this. Give me a value for the divergence. So once we have the value for the divergence, we will move to calculate this delta vector. Okay. J minus half is 0. What is the value of the divergence? That is this factor D. It's 2, right? No, it's 2. It's 2 because if you put in all the values, you find it's 2. Right. 2. So we have d I comma j is k equals to 4. That's great. Okay. So now if we substitute these values, 2 into 0.01 I have, and then I have 0.005 square plus 1.00. So what am I going to get? I'm going to get a value in which I have to put this negative sign in front itself for the delta. Okay. So yeah, that's great. Minus 1.25. That's right. So this is the answer that we are getting. Okay. So this is fairly simple. My advice when we are solving all these questions is to sort of visualize it in such ways it can give you an idea of what the space is. Like this is a 3D space. Right. Right. Okay. So this question is something from your answer from your class only. I'll just hide the answer. So in the simple algorithm velocity correction, this u dash I plus half comma j is expressed as follows, where the standard nomenclature has been used for velocity, pressure, and accompanying coefficients. So we have these four options over here. So which one is right? This is something that was discussed in class exactly. There's no way to go about it. Yeah, that's correct. It's B. B is the right one. So that's all I have in terms of questions for today. Um, the objective is to appreciate that this is an incompressible flow solution methodology, whatever we are discussing now, and that really means that there is no coupling between density and pressure, which forces the researchers to develop creative methods to solve for the equations. So, like in the solar method, they're basically gearing towards uh, forcing a solution which has no divergence, since incompressible flow has no divergence. That's one way to do it. The simple method is basically using an iterative method to keep on correcting the pressure and velocities based on each other such that we get a good solution. And another method which is typically used in order to reuse the code that we have for a compressible, like for example you build a solver which is meant for a compressible flow. So then how do you reuse that entire solver, like whatever code that you have written for in an incompressible flow? So there's something known as modified equation of state. So essentially what you do in that is that you assume that everything is compressible, but for the incompressible media, such as if you have water, you impose a very high pressure on it already. So basically, it becomes functionally incompressible, because, for example, if you have a problem in which both your air and water in reality are at one atmosphere, you just say that actually, like in for computational purposes, you tell the computer that the water has 1001 bar pressure on it already. So this is just something I'm mentioning, if in case you come across it when you are developing something later, that there is an equation of state in which you basically stiffened equation of state is what it is called, in which you manipulate the pressure values on the two types of fluids in the flow to state that one is incompressible and one is compressible. Right. So that was just some extra information, not really required for the course right now. But yeah, they should be able to help you out with whatever the assignment is, and I will close the class.